We are now going to give a closer look at all the available options in the file in the cppdefs.h file. And so I open this file and let's look at the various sections. So this first section concerns the momentum equations, and you can see here, as we already said before, that you have a whole bunch of things that you want to think about, like the advection, on or off advection, the Coriolis terms, the types of advection schemes that you may want to use, which are these, the types of horizontal mixing, and the type of bottom boundary conditions that go from a linear bottom drag coefficient to a logarithmic bottom friction or quadratic bottom friction. Or you may also want to have some sources and sinks of momentum. So this is a section that concerns the momentum, and keep in mind that there are some defaults that are enabled, like for example, in case you don't define any type of advection scheme, the default is going to be the third order upstream bias advection. So you're welcome to keep that as a default. So the next section here, if we go further down, it's going to be relative to the tracer equations, and here we have a whole bunch again of advection schemes that you can use. Even in this case, there is a default advection scheme if you don't select any, which is this one. This TSMP data is something that I'm not quite sure what it is, so I'm not going to comment. And so here are other advection schemes. If you look carefully, you'll find that there are advection scheme for the horizontal, like these, also advection scheme for the vertical, okay, like this one over here. Once again, there's going to be the choice of what type of diffusion horizontal mixing you want to keep, whether it's a Laplacian mixing, which is a del square type mixing, or a del to the fourth type of mixing, which is called the biharmonic. And then there's other things that you can do, like a defined diagnostic run, which means the temperature and salinity are fixed and you're just solving for the velocity, and other things. For example, if you want to define passive tracers, then you can define them like this. Salinity, you have to enable this if you want to use the salinity, otherwise you're only using the temperature. This nonlinear EOS, if you want to use the nonlinear equation of state, the default is the linear equation of state. Then you have these two, Q correction, S correction, which is part of the surface boundary conditions for temperature, the Q correction, and for salinity, S correction. What this does basically, if your surface heat and freshwater flux are not very good, you can enforce some kind of relaxation of the surface salinity or surface temperature to a particular reference value for temperature or salinity. You also can have this thing, solar source, which is defined solar radiation source term. S relaxation, defined as salinity as a freshwater flux. These S correction and S relaxation are kind of similar. We are not interested in the details. And again, you have a source if you want to have a source of heat or fresh water inside your volume. This other section below is concerning the type of pressure gradient calculations. And this is a numerical option, and you can choose various type of numerical schemes, and these are listed over here. They have a reference, so you can look them up. I think the default option is I believe this one over here, which is a good one. But you can check that in the model run, at any given time. When the model runs, at the beginning of the model run, will list the predefined options that are in use, unless you've otherwise modified them. Then we have a section here that concerns like surface fluxes via the atmospheric boundary, and these are things that eventually we'll discuss, in particular the bulk fluxes, which is a way of computing interactively the fluxes from the atmosphere into the ocean. But in our case, when you start, likely you'll start with something simple, and so these are things that are concerned to that, and you can read these in a little bit more depth. And there's a section here that says select model configuration. This typically you care about. For example, if you want to solve the three-dimensional equation, you have to enable this option. Otherwise, you're only going to solve the 2D version of the code, which are the, if you like, the shallow water equations. You also have this option curvilinear grid, which means that you have a longitude-latitude grid, which can be also, not oriented just in the north-south direction, but it could be like have a more fancy shape. this option masking, which we'll use eventually, is useful if you have a land mask, for example, you have a coastline and so forth. Body force, if you want to apply some stresses, body force, and then you have other options like profile, averages, and these are stuff concerning the output, whether you want to write out some of the average files and so forth. You also have options to compute the real-time diagnostic for the biology, for example, for the momentum, U and V, for temperature and salinity. These would be like if you wanted to save, as in addition to the temperature field, for example, if you enable TS diagnostic, you would not only save the temperature and salinity fields, but you would also save, for example, the various terms of the temperature and salinity equations, which could be useful if you want to understand certain dynamics. And then you have ice shelf and other ones. Then we have a whole bunch of options here, for example, for the floats, Lagrangian drifters. Then we have some other options like splines, which is part of the numerics. We have a whole bunch of section here that is for the analytical options. So these are things that you use typically if you are introducing an analytical condition, either initial condition or boundary condition, so forth. So for example, we are going to use, when we do the Coriolis example later, the analytical grid. And so we are basically setting up inside the Fortran code the structure of our grid. Otherwise, if you didn't want to use analytical grid, you would not define this, and the model would try to read, from an input file, the computational grid. This is true also for the initial condition. So if you do analytical, you just put it inside the Fortran code. If not, it'll ask for a file where it can read the initial conditions for the model. And this so is true. So for example, for other surface boundary conditions like this one, which is the surface boundary condition for the momentum, and in this case, these are the wind stresses. Anyway. And we can go on. There's other things that sometimes you care about. For example, how you're going to mix the momentum in the horizontal. You have two options. You can mix along the surfaces, the vertical surfaces of the model, which are not necessarily following a constant depth, and we'll talk about this in some other lecture. And or you may want to mix really along constant depth surfaces and so forth. So you have here again same types of option for the mixing in the horizontal for the tracers. Then this part of section here selects a vertical turbulent mixing scheme. As you know, at the surface of the ocean, you have very intense mixing in the surface mix layer, and often the processes that do the mixing in these boundary layers are not fully resolved by the model. You don't have enough resolution and maybe not enough physics. And so in that case, you have some parametrizations that will produce, a more or less good representation of the mixing in these boundary layers. And here you have a 1, 2, 3, 4 types of parametrization, and you can pick one that you like. And we'll talk about this when we do more realistic applications. These are kind of the core, but you can go on and you can see that there's a whole bunch of other options. These are closure options which are used for, I believe this is for the horizontal mixing. If you don't resolve certain scales in the horizontal, you may also have to parameterize the processes in the subscale, and we'll talk about this in some lecture. And here are still more options, and it gets a little bit more complicated, and you can go through these and read these, and as you go further down, you'll find that there's options concerning boundary conditions, and these are all options, for example, for different type of open boundary conditions, meaning that these would be cases in which your model domain is not closed, but is actually open, meaning there's ocean outside your model domain, and so you have to do something to represent the fact that there's ocean stuff coming into your domain from an ocean that it's not in your computational grid. And so you have to think about how you want to do that, and these are a whole bunch of things. But we'll talk about open boundary conditions when we do the nested, some nested examples. You have also a section on tides that we will look at when we do when we actually going to do a tide simulations, and other options. There's a whole bunch of them here. And so I suggest that you may print out this file and keep it in your notes, and so that you may consult it when you need. So this is just a gross overview of this cppdefs, and in the course of the training we'll learn how to use different types of these options.